Is my screen visible, sir?
Yes, sir.
Yeah. So, very good afternoon. I'm Suresh, Associate Professor in the Department of Robotics and Automation Engineering, PSG College of Technology. So, today's agenda we are going to see about the computer integrated manufacturing. And the introduction about this, first we should know about the business functions because computer integrated manufacturing is the combination of CAD/CAM system and business functions. So first we should know what is business functions and then we will go into the computer integrated manufacturing. So this slide shows that one side is the customer and the opposite side is the industry. So the expectation of customer is that low cost product, high quality and easily available product. So customer is willing to pay for the product as well as industry is expectation is the profit, repeated business and continuous growth. Also the industry is ready to give the value to the customer. So this is the both side balanced system. So how to satisfy the customer and how to become good in a business. So for that we need a computer integrated manufacturing system. So what is manufacturing? The process of converting raw material components or parts into finished goods is the manufacturing that meet a customer expectation or specification of a customers. So this is the general definition for manufacturing. And what is the difference between manufacturing and production? So normally, manufacturing is the process of producing something useful through raw materials with the help of machinery in factories. And there is a huge difference between the manufacturing and production. So the activity of transforming both material and non-material inputs into the output that create utility is known as a production. So here, manufacturing is concentrate only on the material conversion of raw material into a finished goods. So, but production is concentrating on material as well as non-material. So, non-material in the case design, process planning, inspection. So these are all comes under the category of non-material. So this is the difference between the manufacturing and production system. So from where we can start computer integrated manufacturing means first we should know what is CAD. So we all know CAD is a computer aided design. The first source of CAD resulted from attempts to automate the drafting process. Obviously, drafting is a manual process, so we need to automate it. That's why the CAD softwares are developed. So that is the main aim of the CAD software. And these developments were pioneered by General Motors Research Laboratory in the early 1960s. After introducing the CAD, it is more popular after 1970 because of the technological advancements and simplification of the drafting process. And CAD allowed user to design products much quicker without the production of an actual product. So these are the importance of CAD as well as in the beginning of 1980s, computer-aided design program reduced the need for draftsmen significantly. So though that the CAD software is popular in all industries, after the ability to run the personal computers also allowed engineers to do their own drafting work. So these are the origin of CAD. So who are all using this CAD software, computer-aided design? variety of applications we have. So the first one is the architecture, then electronics, automotive engineering also using a CAD software system to design industry vehicles, and industrial design, machinery design, and visual art, and then medical instrument design. So these are the applications of CAD software. So architecture in the case such house planning on a small scale all the way to skyscrapers and kind of building in general. Machinery means creating accurate drawings of machinery parts to check they are fit for purpose, size and function wise. So in the case of considering the medical design, constructing body surfaces in 3D or 2D, example using a 3D brain scans and manipulating into three-dimensional shape for a different view, or the applications of CAD. So here in this example of a house design with both 2D and 3D view, you can see the different tools for viewing the 3D model at different parts are amending. So here the dimension is important one, dimension of a house, as well as the 3D view is used to visualize the art design. So this is example in a civil site. And then electronic design automation. So CAD can also be used to design electronic systems such as printed circuit boards and integrated circuits. So here, as well as designing the layout of circuit, the user can also list logic gates for the circuits. So suppose I can introduce a OR gate. Instead of that, I can use a NAND gate or a AND gate means I can delete the system and then I will introduce another gate with a simple deletion and addition. But in the real case, it is not possible. We can rub everything and then we will introduce another gate. So CAD is popular in industry because of this simplicity. These designs can be used for hundreds of electronic products and machinery. So it is very easy to design a circuit as well as mechanical elements. So this is the example for electronic CAD. See the ICs as well as some resistors and the PCB board is shown here. And some of the uses of CAD with an expert system. The limitations of CAD is that it doesn't incorporate real life concepts such as gravity or friction. So for that we can go with the analysis software, but CAD software mostly is used to design only a product. By using an expert system, it can carry out the calculations such as stress of building or on the drag of a vehicle, or what is the force acting on the body. Everything we will simulate by using the expert system. The use of expert system with CAD can be used with a variety of products such as building materials for buildings, constructions, the design of vehicles, and the design of individual parts. Some examples are shown in this slide. So here the CAD software is used, as well as we have to incorporate the analysis software. The first one is the computational fluid dynamics and airflow analysis. And the second diagram, which is shown in the bottom, is electronic CAD. So this is just introduction about the computer-aided design. In the same way, we have a computer-aided manufacturing. So the CAM, computer-aided manufacturing, is the use of computer software to control machine tools and related machinery in the manufacturing of workpieces. So you all know CAD software is mainly used to only design a product. After designing that, we can do the process planning and then we will do the manufacturing. So manufacturing is an important sector in the world. So how to automate this manufacturing by using a machine tools? That is discussed under the CAM, computer-aided manufacturing. So CAM may also refer to the use of computer to assist in all operations of a manufacturing plant, including planning, management, transportation, and storage. Inventory also comes under the CAM. Workstation to workstation inventory or outside the workstation. Everything is considered as a CAM software. So these are some examples for CNC. So first one is the CNC machine. So here you can see the chuck, turret as well as tool post, tailstock, everything is there. And then we have a panel. In this panel only we have to type a program and then we will run it. So the first diagram is a CNC machine. So here this is the programming panel. Here we can see the simulation as well as program what we typed here. And then here this is the simulation window. So this is the raw material, and this insert tool is used to do the machining operation here. And where to set the X0, Z0 work reference and where is the tool reference, we can see all the simulation by using the screen. And here there is a magazine. In this magazine we have a n number of tools. What are the tools required for this kind of machining operation, we can store it here, and whenever we require we can use the ATC, automatic tool changer, to interchange the tool from machine spindle to the magazine and magazine to the machine spindle. And the next one is the CAD/CAM database. So here I am going to integrate the CAD, computer-aided design, with the computer-aided manufacturing. So this database includes all the data about the product generated during the design, like shape and dimensions, bill of materials and part list, material specifications and etc. It includes additional data required for the manufacturing purposes. The definition, just like a computer-aided design, we have concept of computer-aided manufacturing. So CAD software enables direct link between the CAD and CAM. So on its part, CAD enables automation of designing, while CAM enables automation of manufacturing process. The combination of CAD and CAM enables automated transition from designing to the manufacturing. Obviously, design is initial stage and manufacturing is the next stage. Between there is another stage we will discuss in the forthcoming slides. The database created by the integration of CAD/CAM is also called as a manufacturing database. So generally we will say this CAD/CAM database as the manufacturing database. Here we can take all the data related to our manufacturing and design. So initially this is the traditional design and manufacturing process. So first we need a designer to design a product. After that we will do the prototype, we will make the prototype, and then we will apply the force on the prototype, and then we will check the system will withstand or not. So after prototype testing, then we will go to the process planning. So here we will see what are the process required and what is the process sequence. Everything will be planned here. So that's why it is called as a process planning. After process planning, we will do the production control. Here, what are the facilities required to produce the product? So that is discussed in the production control. What is the cycle time, what is the setup time, and what is the changeover time, and what is the lead time to produce this product. So everything will be planned here. That's why it is called as a production planning. After that, we have a number of machines. By using that machine, we will do the manufacturing operation. By using a human operator, we will do the machining operations. So raw material will enter into the station number 1. After completing all the process, then it will exit in the station number 10. After completing the machining process, it will go to the inspection stage. Here, sample inspection will be done by using the manual operator. So we have an instrument. By using that instrument, manual operator will do the inspection. If it is within the limit, we can accept the product, or otherwise we will reject it. So this is the traditional process of a manufacturer, design and manufacture. So it is our aim to convert this traditional process into a CAD/CAM process. So how to eliminate this traditional process? So for that we have a CAD/CAM process. So design and prototype testing will be taking care of CAD. Process planning, production control, manufacturing and inspection will be taking care of CAM software. So in the next slide we will see. So the first one is the computer-aided design software. Here we can do the design, and then next one is the engineering analysis. So ANSYS, Hypermesh, Nastran, etc., etc. We have a number of softwares to analyze the engineering component by applying the force, by applying the structural conditions, by applying the thermal conditions. So based on that, how the product will be reacted. So that is called as analysis. After completing the analysis, then we will go to the CAM software. So based on the part geometry, it will generate the G codes and M codes and the part program. By using the G codes and M codes, it will generate the part program. So this is called as CAM software. The main important usage of CAM software is to generate a part program based on the part geometry, what we design in a computer-aided design software. So after making the product by using the just G code and M codes, we will make the product by using a CNC machine. After making the product, we can go with the automated inspection. Here we have a camera and the part will be moved in a conveyor. So this camera will capture the image of a product and then it will compare with the master image. So that it is perfectly matching means we will accept the product, otherwise we will reject it. So this system is called as machine vision system. So this traditional process, design, prototype testing, process planning, production control, manufacturing and inspection is converted into a CAD-CAM process by using CAD and CAM software and automated inspection. So this type of system is called as a CAD-CAM process. Here, I will introduce the SIM, Computer Integrated Manufacturing. So it is the approach of using computers to control the entire production process, including design and manufacturing. So SIM integration allows individual process to exchange the information with each other and initiate actions. So SIM is both a method of manufacturing and the name of a computer automated system in which individual engineering, production, marketing, and support functions of a manufacturing enterprise. That's why I told SIM is a integration of CAD, CAM, and business functions. We will see in the SIM wheel. So here, this is also a SIM wheel. So first, raw material will introduce here, or the raw data is introduced here. Based on the raw data, what we are collecting from the customer is converted into an idea by using the designer. After creating the idea, we will do the analysis and then we will make our own model, or we will make a perfect design for the expectation of the customer. This idea and this design will be testing by using the analysis softwares. If this result is okay, then we will move on to the next stage, that is called as manufacturing. Between, we will do the production planning, process planning. So based on the process plan, we will do the manufacturing by using the CNC machine, computer numerical control machines. After that, the final outcome of the product will be ready. So this is the entire process of a SIM. After developing the product by using a CNC machine, then the marketing and business functions also taken care by computer integrated manufacturing. So this is the example for SIM wheel. So first stage is a CAD, computer aided design. So this is called as a design. After manufacturing planning, manufacturing control, and then business functions. So for design, we will use a CAD softwares. So what is geometric modeling and engineering analysis, design review and evaluation. After that, automated drafting. So these are the segments of CAD. So we will see one by one in the forthcoming slides. And then considering the CAM, computer-aided manufacturing, here we have a cost estimation, computer-aided process planning, NC part programming, computerized work standards, material requirement planning and manufacturing resource planning, capacity planning, and etc. So this is the work of CAM, computer aided manufacturing system. And the same way, we will do the process control, process monitoring, shop floor control, and computer aided inspection. This is also a work of CAM. Manufacturing planning and manufacturing control will be taking care of computer aided manufacturing. After completing the manufacturing control, then we will move on to the business functions. So here, computerized business system like order entry, accounting, payroll, automatic bill transfer, automatic accounting, everything will be taking care of business functions. So all these four category is considered in a SIM, computer integrated manufacturing. So these are the tools required for a SIM. So considering the engineering and design, we need a CAD, modeling, finite element method and analysis, optimization and simulation. Considering the manufacturing technology, we need NC machines, numerical control machines, computer-aided manufacturing systems, flexible manufacturing systems, and robotics. So planning and scheduling system plus business functions. So overall, everything is considered as SIM, computer integrated manufacturing. So up to this is the introduction of SIM, computer integrated manufacturing. Then we will move on to the first segment is called as computer aided design. So in this segment, we will see what is design and engineering, and design for manufacturability, computer aided design, computer graphics, CAD hardware and software system, and what is CAD CAM workstations, computer aided engineering, and then CAD CAM integrations and reverse engineering. So first I will introduce a CAD. So computer aided design is the use of computer system to assist in the creation, modification, analysis or optimization of a system. Analysis and optimization of a system design. So here we can create a new design, or otherwise we can modify the earlier design. In the same way, the new design and the earlier design will be analyzed as well as will be optimized by a software system. So that software is called as CAD, computer aided design. So what is the need for CAD CAM? So to increase the productivity of the designer, mainly to increase the productivity of the design, and to improve the quality of the design. So there is a huge improvement in the quality side, because if suppose we are considering the designer and the software design, so there is a huge difference between both. And to improve the communication, so all the data we can involve here. And to create a manufacturing database, it is very easy to create a manufacturing database from the CAD, computer aided design, and to create and test toolpaths and optimize them. So based on the design, we will develop the NC part program, or we will generate an NC part program. So based on the part program, we will optimize the toolpath as well as we will reduce the cycle time or process time. And to help in production scheduling and MRP models, so here both models will be considered: material requirement planning and manufacturing resource planning. So both will be considered here. And to have effective shop floor control, considering the CAD and CAM process, the shop floor will be controlled effective manner. So what is design process? So yeah, design process is a systematic problem solving strategy. So normally design is a problem solving strategy, and with criteria and constraints. We have certain criteria and constraints will be got from customers. Based on that, we have to design a product. Used to develop many possible solutions. So based on the criteria and constraint, we have developed many possible solutions. The developing a many possible solutions is called as synthesis process. After developing the many possible solutions, then we have to narrow down to the possible solutions. With a n number of solutions, We will select only one, or we will combine two uh, possible solutions into one. Like that, we will narrow down to the possible solutions to final choice. So that will be a very good choice of a product. So this is the design process. Is a systematic problem solving strategy with criteria and constraints used to develop many possible solutions to solve or satisfy a customer need or wants, and to narrow down the possible solution to final choice. It is called as design process. This is the definition from ITEA. And who are all developed the design process? So these are the four basic models of design process. Shigley, Pollenbit, Sosiva, and Yarley models are developed for design. So we will see one by one. So what is design process? First we will see, then after that we will see now what is happening now. So this is the Shigley model of design process. So first one is the recognition of need. We have to collect the information from the customers. So that stage is called as recognition of need. What purpose we need to develop a product, and who are all the beneficiary for this kind of product. What is the real need of this product? So that kind of information we can collect it from customers. After that, problem definition. So based on the expectation of the customer, we will write the statement. So that is called as problem definition. Then next process is called as synthesis. I already told synthesis is the process of developing a many possible solutions for the problem statement. I think somebody have raised a question. 1 minute. No. So here the synthesis is the process of developing a many possible solution into a developing a many possible solution is a synthesis. After developing a many possible solutions, we will narrow down to the single solution. So that is taken care by evaluation stage. Then analysis and optimization stage, we will do all the uh, developed design. We can do the analysis to all the design. Then which one is best and best suitable for our application or expectation of the customer? That will be optimized in this stage, that is called as analysis and optimization. After optimizing the design, then we will go to the evaluate. So here we can take the decision this design is suitable for the expectation of the customer or not. So that is called as evaluation stage. If not, we will go to the synthesis again, then we will develop a solution again, and then we will do the analysis. After that we will evaluate. If this design is perfect, it is okay, then we will move on to the next stage, that is called as presentation. So here we can develop the two-dimensional and three-dimensional view as well as assembly view of a expected product. What we developed a product that we can create here. So this 6 stage is called as Shigley model of a design. So first one is a recognition of need, problem definition, synthesis, analysis and optimization, evaluation, and presentation. So all these 6 stages are manual control, but our system is fully automated one. Now we are here to automate this process. How to automate this process? So recognition of need, problem definition, we can't do any automation because we can get the information from the customer, that is recognition of need. Based on the customer expect, we can write the statement, so that is problem definition. So from the 3rd stage onwards, we can do the automation. Sorry. So considering the synthesis process, we can do the geometric modeling. wireframe model, surface model, or solid modeling can use here to develop a possible solutions. If suppose we need to change few changes in the developed model, that we can do by using a geometric model techniques. Or our design is rejected in the evaluation team, then we can modify easily by using this geometric modeling techniques. And analysis and optimization, here also we don't want to make a prototype here. Just do the engineering analysis by using the software like ANSYS, Hypermesh, Nastron, etc. etc. We have a number of softwares. Using that, we can apply the structural conditions, we can see the structural outcome, as well as uh, thermal engineering analysis, computational fluid dynamic analysis, everything we can do by using this kind of softwares. If our system is well suitable, developed system is well suitable for real-time applications, then we will go to the next stage by evaluation. So here also we can fit the constraints. That is called as a design review. We can fix the constraints. If the constraints are okay, then we will move on to the next one. The same engineering analysis software is used here for the evaluation stage. And then presentation stage, we can use a CAD software to develop or to automate the drafting, to generate a 2D and 3D modeling. So this is before CAD. After introducing the CAD, geometric modeling, engineering analysis, design review, and automated drafting are introduced. This is okay, but design process is only to develop a 2D and 3D model. No. So design should taking care of planning for production, planning for distribution, planning for consumption, and planning for retirement. We have to fix the lifetime of the product. Up to that, we need to design. So that's why there's a morphology of design process is introduced. So considering this morphology of design process, so first stage is the primitive need, as I said earlier. So here we have to collect the need from the customer. After that, we have a 7 stages of design. So first stage is a feasibility study or conceptual design. Second stage is a preliminary design or embodiment design. And the third stage is a detailed design. This is what we discussed in the Shigley model. And the fourth, fifth, sixth, and seventh are also a design process, planning for production. Fifth stage is a planning for distribution. And sixth stage is the planning for consumption. Seventh stage is the planning for retirement. So first 3 stages considered as the design phase, and remaining 4 stages are considered as phase related to production and consumption cycle. So we will see one by one. So the phase 1 is the feasibility study to determine whether the need is original, whether it is valid. So we can take all customers' expectation, our customers' data. First, we have to check whether the need is original and it is valid. If so, then we will to explore the design problem generated by the need and to identify its elements such as working parameters, constraints, and major design criteria. What is the working of this design, working of the expected design, and what is the reality and what is the expected product of the design. So that will be discussed in this stage itself, and to collect a number of feasible solutions to the problem. Will it be possible? If suppose I need to write, means we can use a pen, chalk, marker, or anything. So what are all the feasible solution to the problem? If suppose I need to write in a blackboard, means only possibility is a chalk, pen, marker, and everything is not suitable. So here, so we should finalize what are the feasible solution to the problem and sort out the potentially useful solution out of the feasible ones. So this is called as feasibility study. And the second stage is called as preliminary design. To establish which of the proposed alternative is the best design concept. We have a number of concepts. So which one is the best one? From that best one, we can fine tune something. And the combination studies are initiated for establishing the range of major design. So we have a 4 to 5 alternatives. Then we can combine together if it gives the better result. The tolerance and the characteristics of major components and critical materials are investigated and properly fit into the system. If possible, we can get the tolerance values, and if it is possible, then we will incorporate into the system. And the main important one in this phase is the examining the influence of environmental, internal, and external constituents on the system. So, in which environment it is more suitable, and internal and external criterias while it is working. So, everything we should know. Based on that only we can design a product. And project studies are undertaken to study whether the design will meet the customer needs. That also we should know. Testing the critical aspect of the design in order to validate the design concept and to provide necessary information for the subsequent phases. So in the preliminary stage itself, we can fix the criteria and constraints. Based on the criteria and constraints only, we will work on the forthcoming stages. And the next stage is called as a detailed design. In this detailed design, developing an overall synthesis of the design project and preparing a major layout of the system. So preparing specification of various subsystem and components on the basis of master layout. So this is my master layout. Here we have a small subsystems. So first we have to design the subsystems, and then we will incorporate all the subsystems to get the final product. Deciding various dimensions of components. So each and every subsystem we have a dimension. Based on the dimensions we will make an entire product. So the deciding various dimension of the components comes under the detailed design category. Initiating the experiment design by constructing models to check untried ideas. So if suppose is possible, we will initiate the experiment to design constructing models to check untried ideas. So we don't know this may be suitable. This idea may be suitable. So that idea is not tried till now. So we can try the new ideas to the earlier model. Then we can fix the new model if it is suitable. Testing the prototype and obtaining the necessary feedback information based on the redesign and improvements are carried out until well-proven design is accomplished. If suppose the designer is not satisfied or the customer is not satisfied with the product, then we can refine or fine-tuning the product whenever the customer and designer get satisfaction. It is an iterative process. Then the next stage is planning the production process. So preparing the process planning sheet for every part, sub-assembly and final assembly. So here we have a subsystem. By using the subsystem, we have a sub-assemblies, and final assembly we can get by assembling the sub-assemblies. So which part should we make first and which one is the next part? On the first part, what is the first process sequence? We can do the turning, after that finish turning and then knurling. So we can't do the knurling first and then turning operations. So in the same way, we can do the process planning. Based on the process planning, we will finalize the assembly and sub-assembly products. Also, we have to design a tool and fixture. So here, tool and fixtures are the handling devices, and the work holding devices or tool holding devices. If it is not standard one, then we can design our own to fix the tools. Planning to acquire new production or plant facilities. If suppose that facility is not available in your industry or firm, then you can plan your own product and plant facilities. Planning for quality control system. It is a very important one. Based on the quality control system only, our product will be withstand in the market. So the quality control system should be effective one. And the planning for production control, shop floor control. Also, we have to plan. Planning for information flow feedback system. If the feedback system fails, everything will be failed. So we have to formulate this feedback system in an effective manner. And the next stage is planning for distribution. In this planning for distribution stage, we can design the packaging system for the product. So which packaging system is more suitable for your product? That will be fixed in the fifth stage, as well as planning for the warehouse system. Where to store this product, till what time or till what maximum period to hold in the warehouse. So that will be taken care by the planning for distribution team. And the next stage is the planning for consumption. So in this consumption team will design a maintenance period for your particular product, and design for safety. Is your design is safety or not? How to maintain it is in the safety system, and design for convenience for use. Or your product is convenient to use? That convenience you can bring out here. And design for aesthetic features. Also, we have to look into aesthetic way. Then only customer will be attracted on your product, and then they are willing to buy your product. Design for adequate duration of services. So you can plan the maintenance as well as service here in the planning for consumption. And then next one is planning for retirement. In a design phase, clearly mention the usage and lifetime of the product. So how to use your developed product? This is the way you can use our product. That will be given by the planning for retirement team in the product catalog. In the same way, this is the lifetime of the product. After the lifetime, if suppose we are using the product, means it will not give the efficiency. So that we can mention in the product catalog itself. And designing for several levels of use, so that when the service life is reached, higher level of use is terminated and the product can be used less, or you can't use the product. You don't want to use the product. That is the team of planning for retirement work. So these 7 stages are considered as the morphology of design phase. In the same way, what are the benefits of CAD? So first one is the improved engineering productivity. Obviously, to increase the productivity of a design, we will use a CAD software. Also, shorter lead times. If once the design process time is reduced, obviously there is a reduction in lead time, because lead time is from raw material to the shipping of the product, from design to the shipping of the product. so that design time is also value added time, so that it is easily reduce the lead time. If lead time is reduced, automatically productivity will be increased. Reduced engineering component requirements. So if suppose we are doing a manual design, means there is a possibility to add few more components. So software system can eliminate few requirements of the component. Modifications are easier to make. If suppose design a customer expecting something from our detailed design, then we can do the modification easily by using the software systems. Addition and deletion is very simple in the CAD system. So faster response to request for quotations. If suppose quotation is raised by a team, marketing team, then we can easily respond to the request. So this is my duration to develop this product, and I will give you the design within 2 days. That promise we can make. Also minimize the human errors. So by using a software, we can eliminate the human error, or otherwise we will minimize the human error. And improved accuracy of design. So accuracy of design is improved here. In analysis, easier recognition of component interactions. Also provides better functional analysis to reduce the prototype testing. Here we don't want to do the prototype testing. So instead of prototype testing, we can do the engineering analysis. Whenever we require, we can concentrate few forces on the particular area also. That is possible in the finite element analysis procedure. Provides better functional analysis to reduce the prototype testing and assistance in preparation of documentations. If suppose we need to do the 2D documentation or 3-dimensional views, we can easily generate by using this kind of softwares. Design have more standardizations. So here all the standard components we can utilize, because already standard components are stored in the software system. We can use easily. Bolts and nuts are example. Fasteners are example for that. So these are the benefits of CAD. Also, better design can be provided by using the software. Improved productivity in tool design also, not only in the drawing, not only in the product. Also, we can use this CAD software in the tool design, material handling system design. Better knowledge of cost provided, and reduced training time for routine drafting tasks and NC part programming. So NC part programming is automatically generated. No need to write a NC part program based on the part geometry here. So that automatically the time for part programming and then as well as drafting, it will be reduced. Fewer errors in the NC part programming is possible, but manual programmer can change that few errors. If suppose it is a manual part programming, means we can expect many errors. So here only fewer errors are possible. Provides the potential for using more existing parts and tooling. So standard can use it here. And this CAD software helps to ensure designs are appropriate to existing manufacturing techniques. Saves materials and machining time by optimizing algorithms. Assistance in inspection of complicated parts. If suppose we are designing a complicated parts, means it will assist. If suppose whenever you require that assistance, we can get it from the software. Better communication interfaces and greater understanding among engineers, designers, drafters, management, and different project groups. So that is also a possible one. So now we will enter into the CAD software. So first topic in the CAD is geometric modeling or computer graphics. So geometric modeling refers to a set of techniques concerned mainly with developing efficient representation of geometric aspect of a design. Therefore, geometric modeling is a fundamental part of all CAD tools. So here we can develop a product or a part by using this technique. geometric modeling technique. That's why it is the fundamental part of all CAD tools. So geometric modeling is the basic of many applications such as mechanism analysis, mechanism design, finite element modeling, NC part programming, everything we need a geometric modeling techniques. Considering the requirements of this technique, completeness of the part representations, the modeling method should be easy to use by designers. Rendering capabilities also possible by using this kind of softwares. And these are the geometric modeling approaches. So the first one is called as wireframe modeling. The next one is called as surface modeling. And the third one is the solid modeling. Nowadays, we are using solid modeling techniques by using a constructive solid geometry. Also, we have another two modeling techniques like wireframe modeling and surface modeling. This is the difference between three basic geometric modeling techniques: wireframe, surface, and solid modeling. If considering this as the object, and I'm going to cut this object in this way, so we can show the representation of wireframe modeling as the corner dots. And this is the representation of surface model. Only surface is visible. If suppose representation of solid modeling is that the solid way we can represent the model. So the first one is a wireframe model. Wireframe modeling uses points and curves. Only the lines, circles, arcs are shown. But understanding in this wireframe model is very difficult how the part geometries looks like. I will show in the next diagram so that you can easily understand how difficult to understand the part geometry in the wireframe model. The user use edges and vertices of the part to form a 3D object. So here this is a solid geometry. So here it is a wireframe geometry. See here there is a isometric lines are also visible, so that observer can easily confused. So this is the example for the wireframe modeling. So understanding of the part geometry is very difficult while seeing the wireframe model. That's why we are going to the surface model. So here surface modeling is more sophisticated than the wireframe modeling in that it defines not only the edges of a 3D object, but also its surfaces. So here surface is also rendered so that we can understand the geometry of the object. So in surface modeling, objects are defined by their bounding faces. So these are the entities of surface modeling. First one is the analytical entity, and the next one is the synthetic entity. In the analytical stage, we have a plane surface, ruled surface, surface of revolution, and tabulated surface. So in analytical entities, plane, ruled surface, and tabulated surfaces. Synthetic entities, Hermite spline surface, B-spline, rectangular and triangular Bezier patches, Kuhn's patches, and Gordon surfaces. We will see the important entities here. So first one is a plane surface. So see here, this is a plane. So plane having a 2 dimension with a negligible thickness, so that we have planes here. This is the simplest surface in the surface geometry, surface modeling. It requires 3 non-coincident points to define an infinite plane. So non-coincident points to define the infinite planes. So here we need at least 3 points to define a plane. So considering the ruled or lofted surface, this is a linear surface. It interpolates linearly between 2 boundary curves that define the surface or rails than any wireframe entity. So this top one is the rail. Based on the top rail, other columns are formed. So these are the boundary curve. Based on the boundary curve only, other lines are formed. Because of this, the surface is formed easily. Next one is the surface of revolution. So this is an axis symmetric uh, surface that can model axis symmetric objects. It is generated by rotating a planar wireframe entity in space about the axis of symmetry a certain angle. So here, considering this object, so this is the axis and this is the geometry created. Based on this axis, this will be revolved. So that is called as surface of revolution. See here, the object is revolved here so that it looks like a pot. Next entity is the tabulated cylinder. So here, this is the surface generated by translating a planar curve a certain distance along a specified direction, axis of the cylinder. Example. So here, this is the curve generated. So this is the directrix. Based on the directrix, it will be generated the surface. In the same way, this is the curve generated in the second model, and then this is the directrix, so that the surface is formed here. In the same way, this is the curve generated and the directrix is in the opposite side. So from this, the surface is generated. Next one is the Bezier surface. So this is a surface that approximates given input data. It is different from the previous surface in that it is a synthetic surface. Previous one is an analytical surface, this one is a synthetic surface. Similarly to the Bezier curve, it does not pass through all given data points. The Bezier surface allows only global control points. So Bezier curves only focusing on global points, which means that the starting and ending points. It is not focusing on the local points. So please understand that Bezier curve only focusing on global control points. In this example, you can understand that. So P0 and P3 are the global points. P1 and P2 are the local points. So Bezier surface was approximated based on the P0 and P3 only, considering this curve. Considering this one, P0 and P3 are the global points, P1 and P2 are the local points. Based on the P0 and P3 only, the curve is approximated. So Bezier curve only focusing on global points, not on the local points. So here there is a quadratic. So only two global points, and here it is only one local points. Cubic means there is a two global points and two local points. Based on the global points, the surface is approximated like this. And the next one is the B-spline curve or surface. This is a surface that can approximate or interpolate given input data. It is a synthetic surface and it is generally surface like a Bezier surface, but with advantages of permitting local control of the surface. So considering the B-spline surface, it will take global points. Also, it will consider the local points. Based on the global points and based on the local points only, the surface is approximated. See here, this the corners are the global points and the intermediate points are the local points. Based on the global points and the local points, the surface is approximated. That's why all the local points are touched the surface. If suppose it is a Bezier curve, the curve will start from here and then it will approximate it like this. So few local points it will miss. So this is the example for B-spline curve. And this is the example for B-spline surfaces. All the global and local points are approximated and the surface is generated by using the CAD software. And the next one is the solid modeling. Here we have some solid modeling techniques to develop the part geometry. So solid models give designers a complete description of the construct's shape, surface, volume, and density. The first model is the wireframe model. This is the solid model. So you can see the difference between the wireframe and solid model. We can understand the part geometry by seeing the solid model, not by seeing the wireframe model. So in CAD system, there are a number of representation schemes for solid modeling, include primitive creation functions, constructive solid geometry, sweeping, and boundary representations. So these are the 4 methods to develop the solid modeling. So primitive creation functions mean these functions retrieve a solid of a simple shape from among the primitive solids stored in the program in advance and create a solid of the same shape but of the same size. Size is specified by the user. So we can take the geometry here, and based on the size is proposed by a user, it will be approximate. So considering the cylinder, base diameter and the height will be proposed by a user, but the shape is the circle of the base and circle of the top is fixed by the software. In the same way, here the radius of the cone and the altitude height will be given by the user, and the shape will be fixed by the functions. So these are some examples of primitive solids: cube, rectangular prism, triangular prism, sphere, cone, torus, and cylinders. So this is the way how the primitive solids is generated. And the next one is the constructive solid geometry. So CSG uses primitive shapes as building blocks and Boolean as set operators. Here we can use a union, difference, and intersections to construct an object. So this is normally we are using in the solid modeling techniques in the software, SolidWorks or Unigraphics or any kind of softwares. Mostly we are using a constructive solid geometry. We can use extrude command and extrude cut command. By using that, we can generate a solid model. That is comes under the category of solid geometry construction or a constructive solid geometry. So here, this is the square prism is the first body and the cylinder is the second body. So first body is considered as A and the second body is considered as B. So A union B means both solid will be added. And A intersection B means only the common portion is here, other bodies will be eliminated. And A difference B means B will be subtracted by the A so that the remaining portion will be there. Like that, we can use solid geometry constructions. So here there is an A and B. This is the union, subtract, and then intersection. Like this, commands are used to develop a solid geometry. So here we can plan our model strategy before starting creation the solid model. So first we need at least 2 primitive solids, cylinder and rectangular prism. After that we can union it so that cylinder and rectangular prisms are joined. For that we have to select the surface. Then only it will be solved. But I need to remove the hole from the cylinder. Remove some portions from the cylinder. I need to make a hole. So for that I am going to introduce the next cylinder. From this A union B solid, I will subtract this. So this is called as cut. In the same way, I need to produce a slot in the front face so that I will introduce the another solid. So I'm going to reduce this from A union B minus C. So this is also a cut operation. So this combination is called as A union B minus C minus D. Like this, we can develop a constructive solid geometry tree. And this is the next concept, which is called as sweeping. So sweeping is a modeling function in which a planar closed domain is translated or revolved to form a solid. When the planar domain is translated, and that modeling activity is called as translational sweeping. When the planar region is revolved, it is called as swinging or rotational sweeping. So these are the example for the uh, translational sweeping and rotational sweeping. So this is called as extrusion and this is a revolution. So here, these are the examples. So here we can develop this cross section and then we can make it as solid. In the same way, we can develop this section and then we will make it as solid by using revolve and extrude command. And the next solid geometry technique is a boundary representations. So objects are represented by their bounded faces. So here we have a triangular prism, square pyramid or rectangular pyramid. So based on the faces, we will develop the face table, edge table, and vertex table. So first we should know number of faces required, number of edges required, and number of vertices required to develop this geometry. So for that we need to develop a data structure. So this is called as a data structure. So face table F1 is based on the edge 1, edge 5 and edge 6. And the face 2 is based on the edge 2, edge 6 and edge 7. In the same way, edges are framed based on the vertices. So edge 1 is formed based on the vertices 1 and vertices 2. And the vertex 1 is based on the x1, y1 and z1 coordinate system. Like that, from x, y, z coordinates, we will develop the vertex. By using the multiple vertex, we will develop the edges. By using the multiple edges, we can develop the faces. By using the faces, we can develop the solid. For that, Euler equation is used to find out whether this will be a normal solid or not. So these are the closed loop edges, faces, etc. And the Euler equation is called as V minus E plus F equal to 2. V is number of vertices, E is number of edges, and F is number of faces. So these are the way to develop a solid modeling by using a wireframe model, surface model, and solid model. These models are developed by using geometric model as well as it will be analyzed by using the engineering analysis software. For that, we have a separate software. So this is computer-aided engineering. Use of computer system to analyze CAD geometry allows designer to simulate and study how the product will behave, allowing for optimization. So finite element method divides model into interconnected elements. It may be a triangular or quadrilateral elements. Solve continuous field problems. So after developing a geometry by using a geometric techniques, that is considered as a design. So your design will be checked by using this kind of softwares, which is called as computer-aided engineering softwares. So this method is called as finite element method. We are going to divide the entire product into multiple number of finite elements. So each and every element is considered for the analysis purpose. The finite element method is a computational scheme to solve a field problem in engineering and science. The technique has very wide applications and has been used on the problems involving stress analysis, fluid mechanics, heat transfer, diffusion, vibration, electrical and magnetic fields, etc. The fundamental concept involves dividing the body under study into finite number of pieces called elements. Particular assumptions are then made on the variations of unknown dependent variables across the element using so-called interpolations or approximation functions. This approximated variations is quantified in terms of solution values at special elements locations called nodes. And so in this diagram, so this triangular part is called as element and these dots of edges is called as nodes. So here the forces are not concentrated, only here there is a hole, so that the maximum force is concentrated on this area. So I can divide this elements into small parts so that analysis will be more effective in this area. Though this discretization process, the method setups an algebraic system of equation for unknown nodal values which approximate the continuous solutions. Based on the element size, shape, and approximating scheme can be varied to shoot the problems. The method can accurately simulate solutions problems of complex geometry and loading, and thus this techniques has become very useful and practical tools. So this is more widely used. So first we have to take a product, what we are going to analyze, and then we have to apply the load conditions based on the product, where the load is applied in real time. In the same way, we have to apply the load on the software itself, as well as which part is fixed, so that we can place the boundary conditions here. So obtain the stress or strain in the plate is our objective, and then we can divide this entire part into elements by developing the nodes. So nodes are developed so that elements are formed. So here it is a quadrilateral element. So it is approximated method. Geometric model is used here. Nodes are formed first. After that, elements are formed. So here the elements are quadrilateral elements, and meshes are formed, and discretization is also done. So what is the procedure to develop the finite element analysis? So first we have to discretize the product by using the numbering and nodes, that is called as pre-processing techniques. After that, we can select times 315. So select displacement or interpolation model and defining material behavior, derivation of element equations. After that, we can assemble all the equations and then we can apply the boundary conditions. So finally, we can arrive the solutions. After obtaining the solutions, we can do the results. We can take the results from the solutions. So the taking the result from the solution may be a tabular method or a graphical approach. So that is called as a post-processing, and between the last stage to the first two stages is called as analysis stage. So in the discretization of domain, we can discretize the process in which the given body or a domain is subdivided into numbers and elements. So it may be a 1D or 2D or 3D. 1D means line and bar elements, 2D means triangular and quadrilateral elements, 3D means tetrahedral and brick elements are used nowadays. The size of the elements and number of elements will have effect on accuracy and convergence of solutions. If the size of element is small, then the solution will be more accurate with with increase in cost of computations. So that if suppose you need a more accurate solution, means we can make a small elements on the product. So these are the common types of elements used. One-dimensional elements are called as rods, beams, trusses, and frames. Two-dimensional elements means triangular, quadrilateral plates. Elements are considered as two-dimensional elements. Three-dimensional elements are called as tetrahedral, and rectangular prisms or brick elements are considered as 3D elements. So based on the part geometry, we can discretize the total elements. So first one is a one-dimensional frame element, second one is a two-dimensional triangular elements, third one is the three-dimensional brick element. So there is a difference. So here it is in isometric view and this is in a two-dimensional view. That's why this element is discretized by using a triangular element. If suppose this element or this body is in three-dimensional, so we can discretize by using a tetrahedral or brick element. So here the example is a brick element is shown. In the same way, here is a one-dimensional view, so that we can define or we can discretize by using a line or bar. So this is the line element. So in the same way, the triangular elements or nodes are formed here for two-dimensional entity. So in this first diagram shows the discretization with 228 elements. So the next one, there is a central hole, so that we can discretize this whole element into small triangular elements, so that 912 elements are formed here to analyze the entire element. So the next step is the numbering of nodes and elements. So after discretize the entire element, then nodes and elements are to be numbered. So the first one is the concentrated loads on a beam. So that's why wherever the loads are concentrated on the beam, so numbers are developed there. So fixed points are 1 and 4 and the load concentration points are considered as 2 and 3. So in the second one is the abrupt change in loads. So it is not a uniform load, there is a change in load. So we can change, we can number it within the fixed to the free end and then load changing point. Then the third diagram shows that there is a change in cross section. So wherever it is changed, that point is also considered as the point number 2. And the fourth diagram shows that it is a composite wall differential material. So there is a 3 different materials are used here. One is copper, steel and aluminium. So 3 different materials, that's why the 2 different nodes are introduced in between. And these are some examples for a single node element. And the next stage is the selection of displacement functions. In the finite element analysis, assumed the solution function used to represent the behavior of field variables in each elements are called as displacement functions or interpolation functions. So this is developed here in the stage and defining the material behavior. The results from finite element analysis mainly depend on how well the material behavior is accurately modeled, how well you are meshed the final model. The material behavior model is defined by stress-strain relationship and the strain displacement relationship. In the same way, the next stage is to derive the element equations. So you all know the force vector equal to the displacement vector into a stiffness matrix. So the following methods are used to derive the element equations. First, we should know variational method, weight residual method also used for a thermal analysis, and virtual displacement method is used for stress analysis. Energy method also nowadays used to do the stress analysis or a structural analysis. So assembling in the case, we have a force vector and displacement vector and stiffness matrix separately. So I'm going to assemble that the force vector equal to displacement vector into the stiffness matrix. So that's the stage here. Individual element stiffness matrix are then assembled to obtain the global stiffness matrix. So global stiffness matrix, you all know that force vector equal to displacement vector into stiffness matrix of the whole component being analyzed, not only for a single element. Then the next stage is to applying the boundary conditions, the known degree of freedom of the boundary nodes of a physical domain are applied to global equations before solving the global vector displacement. Hence, the number of unknown field variable to be solved will be reduced. So first we have to form the global vector and then we will solve the equations so that we can get the better solution. After applying the boundary conditions, the resulting simultaneous equations are solved by using a Gauss elimination method or any other method also used. By solving the global displacement vector, it is determined so that finally we can take the solution from this vector. And then next stage is the obtaining the required result from the solution. So from the solution of displacement vector, stress and strain values can be obtained. Similarly, the required results are obtained from the displacement vector and they are represented either tabular form or graphical form. So matrix form, it is very difficult to understand the result. So if it is the results are represented in the tabular form or graphical form, it is very easily to understand how the solution is formed. And it is very difficult to understand that displacement pattern, stress distribution, etc. in the tabulated form also, because we have a values. Based on the values, we need to develop a graph again. So representation in the graphical form is widely used nowadays. To overcome these difficulties, the results are usually represented in the graphical form, animated views, and contour plots, graphs, etc. And considering this finite element analysis, the advantages are irregular geometries can be modeled more accurately and easily. Implementation of any type of boundary condition is very easy. Any type of loading conditions can be handled here. The element size can be varied throughout the model. Wherever you require, you can concentrate and you can do the fine meshes there. If not required, you can do the coarse mesh. Whether the problem is linear or non-linear, the basics of FEA remain same. You can solve this as a linear way or non-linear way, but the procedure is same. You can discretize, make a node and elements, and then do the boundary conditions, and then solve the problem. Alternating the element model with different loads, boundary conditions, and other changes on the model can be done easily. But we have some limitations in this software. Disadvantages of finite element analysis. First one, FEA software are costlier. Output result will vary considerably when the body is modeled with the fine mesh when compared to body model with coarse mesh. Of course, because the analyzer should know where to do the fine mesh and where to not do the fine meshes. So that condition analyzer should know. Then only we will get the accurate result. Otherwise, we can't. Even though FEA softwares are used friendly, but they are not relatively easier for use. They should know the procedure, then only it is easy. Otherwise, it is very difficult to form the model as well as do the analysis. So up to this, we discussed about the computer-aided design and computer-aided engineering analysis. Next, we will move on to the computer-aided manufacturing. So here we will discuss detail about CNC machines, CNC program, and classification of CNC machines, and what is CNC dimensioning, how to generate a CNC part program by using the CAM software. So first we should know what is numerical control. So controlling of machine tool by means of prepared program is called as numerical control or NC. So numerical control means it is alphanumeric data. There is the numbers, alphabets, and some special characters may be used to develop the CNC part program. The program consists of instructions such as type of tool to be used, what is the spindle speed you are expecting, and what is the feed rate, and various movements and paths to be followed, etc. In the same way, numerical control can be defined as the form of programmable automation. So considering the automation, there is a three different automations are there. So first one is a fixed automation, then flexible automation, after that programmable automation. So this computer numerical control or CNC machine comes under the category of programmable automation. Numerical control system as a system in which actions are controlled by the direct insertion of numerical data at some point. The system must automatically interpret at least some portion of this data. Then only it will react to the CNC program. So actuator will run. So controller will get the CNC part program and then controller will convert this part program into a machine language, which is zeros and ones, so that actuator will do the machining operations. So these are the basic components of NC machine tool. We need a part program, machine control unit, and processing equipment. In a previous stage, part drawings are typed in a punched tape. Sorry, based on the part drawing, we can develop the part program, and then this part program is typed in a punched tape. After that, we have a tape reader to read the entire part program. Then controller will read the part program, and then it will convert part program into machine language. After that, NC machine tools are used. Nowadays, we don't have a part tape and reader. For that, we have a adaptive control system. So the program instruction is a numerical or symbolic code that is detailed step by step to tell the machine to what to do and how to do the machining operations. The controller unit is the unit that reads the program of instructions and converts into the real movement of a machine tool. Two basic types of control unit are used in the machine tool, open and closed loop system. Hope you all know how to develop the open and closed loop system for CNC machine. And these are the examples for open loop and closed loop system. So without feedback is open loop. Using the feedback, we can control the entire machine tool is the closed loop system. So closed loop system is more suitable for the CNC machines. And these are the history of NC, CNC and DNC. So NC is a numerical control, CNC is a computer numerical control, and DNC is a direct numerical control, and there is another DNC is called as distributed numerical control. In 1959, MIT announces the automatic program tools, which is called as APT programming language. After 1960, direct numerical control will be introduced. This eliminates the paper tape punch programs and allows programmers to send files directly to the machine tools. In 1968, K&T machine tools builders market first machining center. And 1970, CNC machine tools and distributed numerical controls are introduced. In 1918s, graphics-based CAM software system is introduced. 1990s, price drop in CNC technology, so most of the industries utilize the CNC technology. In 1997, PC-based open modular architecture controlled system is introduced. So I told there is a direct numerical and distributed numerical control. Direct numerical control means control of multiple machine tools by a single computer through direct connections in a real time. That is called as a direct numerical control. Distributed numerical control means network consisting of a central computer connected to machine tool, MCUs, which are CNC, is called as a distributed numerical control. So these are the example for direct numerical control, and this is the example for distributed numerical control. So here, computer integrated manufacturing host database is there to control all the machine tools, and the local area network is utilized to control the entire system. So these are the examples for DNC, distributed numerical control. There is a file server. By using that, there is a hubs to transfer the data to the various machine tools. And this is the computer numerical control definition. So CNC as the numerical control system wherein a dedicated stored program computer is used to perform some or all other basic numerical control functions in accordance with the control program stored in the read and write memory. So as earlier I told, so CNC machine tool having a part program. So that part program is alphanumeric data. This alphanumeric data is used to control the entire machine tool in the CNC machines. So this is data processing in CNC machine. So we have a servo motor. Also we have a table motion. So for that we have a rotate ball screws or a linear guideways to guide the machine table. And this is the right hand thumb rule to fix the coordinate system. So one is for vertical machining center and another one is for horizontal machining center. Both machining center, the z-axis is in a vertical means, so that is considered as the vertical axis, vertical machining center. If the z-axis is in the horizontal means, that is considered as horizontal machining center. That will be explained in the thumb rule. So types of CNC machines. So these are the classification of CNC machine based on the motion type, based on the control loops, power supply, positioning system, and axis or coordinate system. So based on the motion type, first point to point, straight line path and continuous path. Based on the control loops, it is open loop and closed loop. And based on the power supply, it is electric, hydraulic and pneumatic supply. And based on the positioning, it is incremental and absolute. And based on the axis of a system, machining center is horizontal and vertical. Also, we have a turning center having only 2 axes, not a 3 axis. So these are some example for point to point, continuous path and contour path. First one is the point to point. Second one is the continuous path and the third one is the contour path. Based on the positioning system, we can classify as absolute and incremental. All coordinate values are relative to fixed origin of the system, means that is absolute, and all the points, every measurement refers to a previously dimensional position, means that is called as incremental. So we have to write a CNC program based on absolute or otherwise on the incremental system. So next we will see the NC dimensioning. So this is the basics and fundamentals for CNC program. So we should know what is NC dimensioning. Based on that only we can write a CNC part program in all 3 axes. So 3 axes is basic requirements to do the machining operation in the machining center, and 2 axes is required to do the machining operation in the turning center. And here you can understand the machine you will be working with. So this is the CNC machine. We have a CNC machine with panel board and other mode switches. Also, we look at the machine from the programmer's viewpoint, as well as you have to look at the machine from the operator's viewpoint. Then only we can write the effective part program. So this is the example for a universal slant bed turning center. So here we have a chuck which is connected in the machine spindle. This chuck is a work holding device which is used to hold the workpiece in the jaw. Also, we have a tailstock. This tailstock having a 3 different component. One is dead center, quill, and then body of the tailstock. And then we have a turret. In this turret only we are going to store the tools. What are the tools we require to do the machining operations? So these are the components of a body. This is the Z axis. So towards chuck is Z minus, and towards tailstock is Z plus, and towards floor is X minus, and towards sky is X plus. And this is the axis classification for machining centers. So Z axis is vertical, so this machining center is called as vertical machining center. X plus, X minus, Y plus and Y minus. So here 3 axes are required to do the machining operations. Minimum 3 axes is required. And this is how the machine 0 point and work 0 point are located in the vertical CNC machining center. And these are some example. And this is the absolute positioning and dimensioning. So here in this point is the origin for all the corresponding points. But in the incremental system, so this is the first origin. After moving the tool to the B, then the work origin will be shifted to the B. So here X and Z are 0. After moving the tool here, then the work origin also shifted to the new position. So this kind of positioning system is called as incremental dimension. Also, we have a reference 0 and reference points on a CNC machines. So we have 4 reference points in a CNC machine. Obviously, programmer will use only 2 reference points manufacturer will fix another two reference points. So machine 0 point is considered as M, work 0 point is considered as W, reference point for the tool is considered as R, and the tool reference point is considered as E. So here M and E are fixed by manufacturer. So as a programmer or a worker, we can't change this reference. It is fixed by manufacturer of the machine tool. And W and R is fixed by the programmer so that we can change wherever you can require. At that time, you can change the W and R. So these are the three axes in the vertical machining center, X, Y, and Z axis. And this is the part that's required. And basic machine axis are three axes, so X, Y, and Z. In the same way, we have an additional axis, A, B, C. So A axis is the angular axis about X axis, B axis is the angular axis about Y axis, and C axis is the angular axis about Z axis. In the same way, we have a U, V, and W. So U is the secondary axis parallel to X, V is the secondary axis parallel to Y, and W is the secondary axis parallel to Z. So obviously there is a 9 axis of CNC machine is possible. So milling machine with the 4 axis is shown here. So W is shifted here so that this is the additional axis. NC part program. Before enter into the part program, I can show one video so that you will understand better about the part programming. See how this CNC machines are utilized to make the axis asymmetry components. So this is the raw material which is located on the work table, and this is the cutting tool. Material used here is aluminum A7N01. This is the use of CAD software and CAM software. They integrated both CAD and CAM software together, so they will do the machining operations. So this video you can get a better idea. So now we will enter into the NC part program. So these are the basic programming commands. So we need a motion commands, plane selection commands, positioning system selections, unit selections, work coordinate setting, reference point to return and return from reference points, tool selection and change of tools, feed selections and input for the feed, spindle selections and miscellaneous functions. So normally G codes are called as a geometric code and M codes are called as miscellaneous codes. So mainly G codes are concentrating on geometry of the product and M codes are concentrating on the machine commands. And before entering into the program, we should know what is compensation and what is offset. So the use of compensation and offset functions in defining work coordinate systems, performing tool diameter compensations or cutter radius compensations, and accommodate tool length compensations also often results in reduce the programming effect. So main compensation and offset functions are work coordinate compensation, tool diameter compensation, and tool length compensations. So these are the commands used for a cutter radius compensation as the G40, 41 and 42. 40 is to cancel, 41 is right and 42 is left. Tool length compensation are G43, 44 and 45, vice versa. And to reduce the number of lines in the CNC program, so we can use the fixed cycles. The purpose of a fixed cycles is to execute a series of repetitive machining operations with a single block command. Fixed cycles may be classified into the following three categories: standard, special, and user-defined fixed cycles. So normally, if suppose it is a manual program, means we need to write a number of lines in a CNC program. We need to reduce the number of lines. So for that, what we can do is we can use a fixed cycles. If suppose we are using a CAM software, means it will generate a part program automatically based on the geometry what we given in the CAD software. So for that conditions, we no need to use the fixed cycles because it is generated one. So we will see G codes one by one. So for G00 is a rapid traverse, 01 is a linear interpolation, 02 is a circular interpolation clockwise. If suppose you need to move the cutting tool in a CNC lathe or a machining center in a clockwise direction, you have to go the command G02. In the same way, it is a circular interpolation in the counterclockwise means G03. Dwell, normally mechanical engineers are well known about the dwell period in a CAM profile. In the same way, here also it is a waiting time. In a CAM profile, the follower is waiting in a particular manner. Here, the program will wait without any operations. So for that kind of time delay, we can go the Z04. 17, 18 and 19 are the XY, XZ and YZ plane selections. G21 is inch input and G22 is a metric data input. So G00 is a rapid traverse. So here machining operation will not be done. Only tool will move in a rapid way, very fast. So G01 is a linear interpolation and circular interpolation. Tool will move in the clockwise direction, and G03 it will move in the counterclockwise direction. At 21 is the metric data input, 28 is return to reference point, 29 is return from reference point. Wherever you require, you can place the tool. And G40 is cutter compensation cancel, 41 is left and 42 is right compensation. 43 is length compensation plus, 44 is length compensation minus, 49 is to cancel the compensation, length compensation. And here there is a fixed cycle, 73 is high speed peg drilling, 80 is canned cycles, cancelling the canned cycles, 81 is a drilling cycle, 82 is a counter boring cycle, 83 is a deep hole drilling cycle, and G90 and 91 is for dimensioning or questioning system, 90 is for absolute questioning, 91 is for incremental, 92 is for re-questioning the origin point. Normally, we will fix the origin point at the center while considering the CNC lathe. At the edge and the center, we can fix the X0, Z0. If suppose we need to shift the origin point, means we can use the 92. And 97 is revolution per minute, 98 is feet per minute, 99 is feet per rotation. In the same way, miscellaneous command M01 is optional program stop, M02 program end, M03 spindle on clockwise direction, M04 is spindle on counterclockwise direction, M05 spindle stop, M06 tool change command, M07 miscellaneous coolant on, M08 coolant on, sorry, M07 is missed coolant on, M09 is coolant off, M10 is clamps on, M11 is clamps off. And the program end we can use M30, subprogram call, M98, and return to main program is M99. This is how the machine tool will run. Common block format. Here we have a sequence number, preparatory function number, G0 commands, dimension words, X, Y, and Z axis command. Dimensions will be given here. And the feed rate. What is the feed rate to work the entire machine tool? That should be given in the program block. And spindle functions is in S 1500. Tool functions also we have to give which tool should perform the machining operation. That will be fixed here. And miscellaneous command M03. Spindle on clockwise is M03. So all these lines are considered, all these data are considered as a single word or individual word. So here in the PLC program, each and every line of PLC program is called as rung. In the same way, CNC program, each and every line is called as a block. So this is for a part program. We have to write up G codes based on the part geometry. We have to give the dimensions. This is for example, I'm showing the part program. And this is the next example to show the part programs. Here are some examples. How to write a CNC part program. Without cycles, here I used 20 lines or 20 blocks to write a CNC part program for this geometry. In the same way, if suppose 2 or 3 operations are involved, we will write this in a 200 or 300 lines with considering the depth of cut. This is for machining centers. We can fix anywhere in the work origin. Based on that, we can write a CNC part program. This is for this geometry. And we will see one by one in the cycles. So first cycle is a turning cycle. So G70 is for finished turning cycle and G71 is for rough turning cycle. So in the rough turning cycle, it is a 2 block series. So first series we have a U and R, and second series we have P, Q, U, W, F, and S. First block U and R is the depth of cut and retract height. What is the depth of cut for this particular operation? And after reaching the end point, the tool should move upward. That height is called as retract height. In the second block, we have a P, Q, U, W, F, and S. So P is the contour start block number, Q is the contour end block number, U is the finishing allowance in X-axis. Once this operation is carried out, the edges of the workpiece is small edge corners are there. So we need to remove it. For that, we will give the allowance in X-axis as well as in Z-axis. So that will be given as U and W. So F is the feed rate for this particular operation and S is the spindle speed for this particular operations. And G70 command, we can give a P and Q, just the start block number and end block number. We can change the tool and then we can give the start and end block number. Then only it will perform the finishing operation. So this is just an example for rough turning cycle. 2 block. This is how the operations will be carried out. So this is the cutting tool. So this cutting tool will first start here, then it will pass up to this edge. So this is the first pass. After that, there is a retract height. What we are giving in the R is a retract height, and then it will move to the rapid traverse. Then it will enter down. So this is the depth of cut. Again, that is the second pass. Then it will move upward is the retract height. Then rapid. Again, next pass. So number of passes required to develop this geometry is 10, based on the depth of cut and retract height. And this is the allowance given here. U is 0.1 and W is 0.1. So U is the x-axis allowance and W is the z-axis allowance. And the next cycle is called as a peg drilling cycle. So G74 is the code for peg drilling cycle. R is the retract height. X is the which is the position of a hole, and Z is the depth of the hole, and Q is the depth of cut in each pass for in a micron. So this should be given in the microns, not in mm. And then feed rate for this particular operation. So this is the peg drilling cycle. So first it will enter, tool will enter into the workpiece up to this distance, and then it will go back. Again, it will enter into this distance, and then it will go back. So this peg increment is given in the Q, that is depth of cut, and then retract height is 1. So 0.5 mm it will drill. After that 1 mm it will go back to remove the chip. Again 0.5 mm it will move inside, and then 1 mm it will go out. So this kind of operation is called as peg drilling. So here also G74 code is used, and 2 block series. And the next one is a grooving cycle. So G75 code is used for a grooving cycle, and this is also a 2 block code. So first one is a relief amount or retract amount, and then second block there is a X. So this is the finished diameter dimension, and W is the final Z position of a groove from the initial position to the final position. So that what is the dimension it should move, tool should move, that will be given in the W in minus. Then the next one is a P and Q. So P is a peg increment. So x-axis increment is called as a peg increment, and z-axis distance is called as a stepping distance. So x-axis distance is given in P, and z-axis distance is given in Q. And F is the feed rate for this particular grooving operation. And this is the illustration of a grooving operation. So this is a cutting tool, and vertical movement is called as stepping distance, and then horizontal movement is called as peg increment. And the next cycle, that is the last cycle, is called as thread cutting cycle. So here this is also a 2 block. The code is for this thread cutting cycle is G76, but it is little lengthier process. So first 6 digit is given in P, that is called as first block parameter. So first 2 digit from the last first 2 digit is considered as thread angle, and the next 2 digit is called as pull out angle, and the last 2 digit is called as number of passes for finishing operation. So here number of passes for finishing operations is 3. Pull out angle is 15. After reaching the end point, the tool should move 15 degree and then it come out. And the thread angle or included angle for this threading operation is 60 degree. And Q is the minimum depth of cut, which is given in the Q, that is in micron, and R is a finishing allowance, that is 0.15 mm is the R. In the next block, X is given in X is the core diameter. So here M12 thread is formed, but the outer diameter of the that is a major diameter of the thread is 12 mm, but here we should give the minor diameter, which is called as a core diameter. And length of the thread is given in Z parameter, and the height of the thread in microns is given in P parameter, and the depth of cut of first pass in microns is given in Q parameter, and pitch of the thread is given in the F parameter. Up to this, F is the feed rate. In a thread cutting cycle, F is the pitch. That is the difference in threading cycles. So you all know this is the nomenclature of a thread. So here there is a chamfer. This portion is called as a flank, and center to center distance of 2 thread is called as pitch, and this angle is called as included angle, and this is the root. This diameter is considered as a minor diameter, and the major diameter is the outer diameter, So this minor diameter and major diameter are concentrated here. Major diameter is given in the M12, but in the threading operation in X parameter, we can give 9.853 is the core diameter, which is called as minor diameter. And this is how the threading operation is carried out in a CNC machine. So first threading tool will rapidly come to this point. After that, it will form the thread and then it will go out. So the length of the thread, minor diameter and pull out angle, everything is shown in this diagram. Based on the parameter dimensioning, it will do the operation. And this is some example for a CNC program. So here there is a 3 operations. One is turning operation. So here we can do the rough turning and finish turning. After that, grooving and then threading. So command used for this particular operation is G71, G75 and G76. So this is the part program developed in this by using this geometry. So we have no time to explain this program. So next one is a subprogram. So M98 is a subprogram call. M99 is a return to main program. So here P of 4 digits are indicated in the O of 4 digit in the program being called. So O is the main program, P is a subprogram. So these 4 digits are used to call the subprogram. So in this example, you know M98 is called subprogram. So 2000 is the program number, which is denoted in P. So O2000 program will be called here. After that, after completing the subprogram, then in the end of the subprogram, we will write M99. So it will return to the main program of the next line. That is illustrated here. This is the main program. So in this case, there is a 4 digit. 1010 is a program number, but initially there is a number 2 is inserted here, which means that this subprogram will run 2 times. After that, it will return to main program. So here only 4 digits are given. 1020 is the program number. So it is denoted as O1020. It will run once and then it will return to the main program because the subprogram last line is M99, so return to main program. And the next cycle is the drilling cycle. X, Y, Z axis are required here because this will be done in the vertical machining center. R and F are the another parameters. So X, Y, Z are the whole position in X axis, Y axis and Z axis. And R is the position of our R plane. We have to fix this R plane anywhere you want. But closer to the work surface is which is most optimum to reduce the cycle time. So that we can fix the R on the work surface with a closer dimension. And F is the feed rate for this particular operation. So this is some example for the program. So based on the program, you can draw the geometry, or based on the geometry, you can write the program. So here there is a CNC part program using subprogram. So based on the geometry, we can use the main program, and then we will call the subprogram M98 here, and then in the last subprogram last line M99. So it will call this program and it will run again, return to main program. After changing the tool, again we will call this program and then return to main program. The whole position dimension is mentioned in this subprogram. So the next one is the CAD/CAM process. So SIM is the computer integrated manufacturing. Integration of CAD, CAM and business function is the SIM. So now how to integrate this CAD and CAM? We elaborately discussed about the CAD and CAM. So now we are going to integrate this CAD and CAM process. So we have a CAD/CAM system to develop the geometry. So CAD system is used to develop the geometry. After that, a geometry is created. Based on the geometry, we can optimize the toolpath. After optimizing the toolpath, we can generate a part program by using the CAM software. This part program will be sent to the CNC controller. So based on the controller, based on the CNC part program, controller will convert this part program into a machine language. So zeros and ones will be sent to the actuators, controls and drives so that it will be activated. So machining operations will be done in a machine tool. Finally, we will get the product. So this is the integration of CAD and CAM process. So these are the need for CAD CAM process to increase the productivity of the designer, to improve the quality design, to improve the communications, create a manufacturing database, test tool paths, and optimize. Okay. This is some example. So first is CAD model to CAD, CAD to process planning, and CAM workstations. This is how the CAD CAM and SIM is evaluated. So 1950s, 1960s, 17s, and 18s onwards, the SIM was widely used. So these are the integration stages of SIM: strategic level, operations level, technological level, and behavior level, and organizational level. Considering the SIM, we have a CAD CAM process. In this, we have a production control also. So considering the production control, we need to know few important topics. The first one is the reverse engineering. Why we need a reverse engineer? We have already product. So we need to do the similar kind of product by using the already existing one. A systematic methodology for analyzing the design of an existing device or a system, either as an approach to study the design or as prerequisite for redesign. So in this component or a product, maybe your competitor's product. You can take the product and then see what are the things used inside it, and then we can make our own product based on the competitor's product. And then reverse engineering helps to develop the systematic approach to thinking about the engineering design of devices. If suppose it's your competitor's product, then you can develop your own product by using the reverse engineering concept. And these are the levels of analysis of reverse engineering: system-wide analysis, subsystem dissection analysis, and individual component analysis. We have no time to discuss each and every stage here now. Then I will move on to the example component. So this is the reverse engineering physical product, then obtaining the dimension details from the product, and then we can make our own 3D model by introducing few changes in the model. After inspecting the model with the physical model, then create a manufacturing drawing. How to manufacture, what are the facilities required. Based on that, we can create a model. After that, process for manufacturing. What are the process required and which machines are suitable to do the process, so that we can do in this stage. So finally, we can do the machining operation by using that kind of product. So why do we need reverse engineering? What are the benefits? So first one is to saving the cost, maintenance cost as well as developing cost, and the quality improvements and the competitive advantages. So these are the main needs of a reverse engineer. Then we will see our production planning and control to deliver goods in required quantities to customer in required delivery schedule without any delay. So we can deliver the product at a particular time manner. To ensure maximum utilization of all resources, we have a lot of resources available in our industry. So we can use all the resources without any delay. We can supply the product to the customer. To ensure production quality products, to minimize the product cycle and lead time, to maintain optimum level of inventory. So you all know that inventory is one of the major modal in the lean manufacturing. So obviously we need to eliminate the inventory, but it is not at all possible considering a few cases, so that we can at least reduce the inventory. To maintain flexibility in manufacturing operations, coordinate between labor and machines and various supporting departments. And the next important one is the sequential engineering and concurrent engineering. So sequential engineering, traditionally the design and manufacturing phases were separated and occurred sequentially. The product design department develops a new design without considering the manufacturing department. In the same way, the design engineering department completes the design, it throws the drawing to the specification, throws the drawings and specifications over the wall to the manufacturing department. Manufacturing departments also doesn't know what is written in this document, so they will do the manufacturing process and they will send it to the sales department. Sales department will sell the product to the customer, but customer is not satisfied because of your product errors. So customer will send to the sales department, then it is comes back to the manufacturing department, then it goes back to the design department. So this is how the sequential engineering is works. So this is generally called as over the wall engineering. So we don't have a contact between marketing people to design, design to manufacturing, manufacturing to sales. But our aim is to break this wall between the segments of design, manufacturing, and sales and marketing. So just developing a new product and throw it to the manufacturing is nowadays it is not a valid solution. So these are the weakness of the sequential engineering: insufficient product specifications leading to an excessive amount of modifications. Not only modifications, also we are spending a more amount of the design development. Little attention to the manufacturability issues of the product at the design stage. Late changes usually leads to expensive changes to tooling and other equipment. So we need to avoid the sequential engineering. Over the wall engineering concept is not suitable for sim environment. So we can go with concurrent engineering. Normally, the concurrent engineering is called as a simultaneous engineering. It performs a product design and process design. Typically, concurrent engineering involves the formation of cross-functional teams. This allows engineers and managers of different disciplines to work together simultaneously in developing a product and process design. So this is the definition for concurrent engineering. So concurrent engineering methodologies permit a separate task of the product development process to be carried out simultaneously rather than sequentially. Product design, testing, manufacturing, and process planning through logistics, for example, are done side by side and interactively. Potential problems in fabrication assembly support quality are identified and resolved earlier in the design process. So in this way, design concurrent engineering is taking care. So we will club together all the team members and then we will design a product. So we will achieve a quality as well as effective product from the team. So concurrent engineering also called as simultaneous engineering, concurrent design, life cycle engineering, integrated product development, and team design. So these are some illustrations of concurrent engineering. This is how concurrent engineering has developed a product. And this is the difference between the sequential versus concurrent engineering. So sequential engineering is a traditional process that is a linear way of product development, and concurrent engineering is a team collaborations. So we will call all team members and we will sit together and then we will develop the product. So that is called as effective product development. So these are the importance of concurrent engineering stage. In the same way, concurrent and sequential engineering product life cycle development is shown in here. These are the objectives of concurrent engineering: decreased product development lead time, improved profitability, greater competitiveness, greater control of design and manufacturing cost, close integration between departments, improved product quality, promotion of line split, enhanced reputation of the company and its product. So considering the product development cycle, you all know this is the idea generation is the first stage, and then screening the idea, concept development and testing, marketing strategy development, business analysis, product development, market testing, and commercialization. So these are all the stages of new product development process. Initially, the cost for the sales is a little less, but the profit we are expecting is also based on the stages. First introductory stage, we can expect the profit. And growth stage, there is a profit. Also, we have a maturity stage. In that maturity stage itself, we can design or we can refine the earlier design. After that decline stage, so here we can't export the product. So your new product will enter into the stage, then only we will achieve the continuous growth. And the next one is called as a cellular manufacturing, a lean manufacturing approach that helps companies build a variety of product with as little waste as possible. I already told Muda is a waste in a value stream. So elimination of waste is the concentration in lean manufacturing. So equipment and workstation arranged in a sequence that supports smooth material flow through the process with minimal transportation or delay. Derived from the word cell. So these are the examples for the cellular manufacturing. And high variety production is the benefits of cellular manufacturing and one piece flow. So normally, suppose you need to balance the uh, life work line. So we need to implement this single piece flow or one piece flow concept in an industry. Then only the line will be balanced in a smooth way. Otherwise, one operator will get free space and another operator will work in a hectic way. So like this, we can make one product and then move it to the next workstation so that the line of the workstation will be balanced effectively. The next important one is the process planning. I already told process planning is the bridge between design and manufacturing. So the function within the manufacturing facility that establish which process and parameters are to be used to convert a part from its initial form to a final form predetermined in engineering drawing. So this is how the process planning is developed. So these are the functions of process planning: raw material preparation, process selection, process sequencing, machining parameter selection, tool path planning, machine selection, and fixture selection. So considering the computer-aided process planning, we have two approach. One is variant approach, another one is generative approach. So variant approaches is the group technology based, computer aids for editing and parameter selection. Generative approach, some kind of decision logic, decision tree table, artificial intelligence, objective oriented, and skill experience. These are the requirements for the manual processing. This is how the process plan sheet is developed by using the facilities as well as part geometry. So part geometry is given. Based on the part geometry, we need to develop the setups as well as a process. There are some example products to develop the manual process planning. And computer-aided process planning, the first one is a computer-aided process planning, CAPP, and these are the benefits of CAPP. The first approach is a variant approach. So from the part geometry, we can develop the group technology code, process plan, and then this is the general approach for the process plan. And MRP1 and MRP2, material requirement planning and manufacturing resource planning. This is the objective of MRP, provide right parts at right time to meet the schedules for completed products. So we need to develop the manufacturing resource planning and enterprise resource planning. ERP is called as enterprise resource planning. Nowadays, SIM technology is used full of ERP system. This is called as a group technology. So group technology was introduced by Frederick Taylor in 1919 as a way to improve the productivity. Generally, the group technology is the manufacturing philosophy that seeks to improve the productivity by grouping parts and products with similar characteristics. If suppose a shaft is there, means we can group similar kind of shafts or similar kind of fasteners together, so that it is comes under the group technology category. Into families and forming production cells with a group of dissimilar machines and process. So GT can be defined, it is the realization that many problems are similar and that by grouping similar problems, a single solution can be found to set of problems, right? In the same way, we can group a similar kind of products so that this is the manufacturing solution for a set of products, so that we can arrive the solution easily as well as quick as possible. So these are some examples of a part family. If suppose we are grouping together, that is considered as a part families. Group of similar parts is known as part family, and group of machineries used to process an individual part family is known as machine set. And coding and classification, considering the group technology, the important thing is called as a coding and classifications. How to classify the part family, that is called as coding. So here Optis classification system, it is developed in the German and widely used in industry, and it provides basic framework for understanding the classification of coding process. So normally this is the 9 plus 4 digit, so 13 digit code system. First 5 digit is for form coding, and second 4 digits are used for supplementary coding, and the letters are used for a secondary coding. All full of this coding systems deals with the manufacturing information as well as design too. So for this is the 16 digit I already told, 13 digit. For focusing on form geometry dimensioning feature relevant to part design, supplementary codes are here and secondary codes. So based on that, this is how the basic structure of Optis coding system. So what is the part classification and what is the main shape of the part, and it is a rotational machining or a plane surface machining or additional holes or teeth are unformed. Based on this, we can take a coding as well as supplementary codes like dimensions, materials, shapes and raw materials and accuracy. So based on this, we can write a code and we will store it. So based on the code classification system, we will take the product and we will use the manufacturing solutions. And these are the form codes. So for this kind of product, there is a thread and there is a deep hole. So based on that, we will form a code. Length to diameter ratio is 1.5, so digit 1. External shape is both ends stepped with screw thread on one end, so that it is digit 2. Internal shape is part contains a through hole. So digit 3 we can take as 4. Plane surface machining is none, so we will take 0. There is no auxiliary hole, gear, teeth, etc. So we can take that as 0. So the form code for this particular geometry, Optis, based on the Optis classification system, is 1500. Like this, we can make a product. And then the next one is the flexible manufacturing system. So a system that consists of numerous programmable machine tools connected by an automated material handling system is called as flexible manufacturing system. So these are the basic components of FMS: workstations, automated material handling storage system, computer control systems and workers. Based on the product volume and product variety, we can characterize the FMS. These are the flexibility and different types of FMS: sequential, random, dedicated, engineer and modular types. These are the FMS layouts: closed loop layout, robot center layout, ladder layout, open field layout, and the line layout. So line layout is first one, and then loop one, open field, and then robot center. So these are the factors influencing the FMS layout: available raw materials, proximity to market, transport facilities, availability of efficient and cheap labors, power, and objectives. These are the advantages and disadvantages. Considering the material handling system, these are the principles of material handling system: reduce unnecessary movement, reduce obstructions and bottlenecks, scientific factory layout, use of standard material handling equipments, plan a minimum number of loading and unloading system, use a gravity to transport material rather than the power. If it is not power, we can use the, if it's not possible, we can use the power system. So conveyors are the one of the material handling system. These are the types of conveyors. And ASRS, automated storage and retrieval systems, or handling systems. After that, we can see the AGVs, automated guided vehicles, are one of the material handling system. And these are the data collections method used in a SIM. So barcode technologies, optical character recognition, vision systems, RFID, magnetic identifications, voice technology, and sensor technology are used to collect the data in a SIM environment. So if you have any doubt, you can ask now. Okay, thank you.